All right, so here are the rest of the examples from class today having to do with integrals with the natural log. So we kind of left off in class saying that generally we like to look in the denominator for what we want to set u equal to. So example 3, I'm going to set u equal to 1 plus cotangent in x. And my derivative, this is where you want to brush up on your trig derivative rules, is going to be negative cosecant squared. And then when I solve for my dx, that's going to be negative du over cosecant squared of x. And then I'll go ahead and do my substitution. So the integral of cosecant squared of x over u times negative du over cosecant squared. My cosecants will cancel. I can pull out that negative 1 as my constant on the outside, and that leaves me with 1 over u du. So then my integral here is going to be negative 1 times the natural log of the absolute value of u plus c. And then I can go ahead and replace my u. So negative ln of the absolute value of 1 plus cotangent of x plus c. All right, so we'll look at one more kind of just integral problem, and then we'll look at a couple of applications here. So example 4 is going to be a little bit different. This is going to involve a couple of steps in order to do our substitution. But again, I'm going to look in the denominator and I'm going to say, okay, well, I'm going to set my u equal to that stuff that's being squared. So I'm going to say u is going to be equal to x plus 1. And that gives me a du equal to dx. Go ahead and do that substitution. So 2x over, this time it's going to be u squared times du. And the problem here is we still have an x and we still have a u. So this is where we're going to want to go back and manipulate our u is equal to x plus 1 so that we have something to substitute up here for this top x value. So I'll solve this one for x. It's going to tell me x is equal to u minus 1, and I will go ahead and substitute that into my numerator up here. So 2 times u minus 1 over u squared du. And I could go ahead and distribute this 2 out, but I could also think about it as a constant, because we could also write this as 2 times u minus 1 over u squared du. And I can actually pull that on the outside of the integral, which is actually probably going to make my life a little bit easier. So I'm going to go ahead and do that. So at this point, I'm going to just manipulate this a little bit algebraically, and I'm actually going to split this up into 2 fractions on the inside of my integral. Move up here. So 2 times the integral of, I'm going to do u over u squared, and then minus 1 over u squared du. And I'll simplify that. So that's going to give me 2 times the integral of 1 over u minus 1 over u squared du. And I know that this is going to give me the natural log stuff because that's my 1 over u. And here, I would probably rewrite that as a u to the negative 2, so I can just apply my power rule to that. And then I can go ahead and do my integration here. So 2 times, and I'm going to have the natural log of the absolute value of u. And then I'm going to apply my power rule here. That's going to be negative 1 over negative 1, u to the negative 1, plus c. And I'll just clean that up a little bit. So it's going to be 2 times ln of the absolute value of u. That's going to become a plus, and then that u is going to drop down into the denominator, so 1 over u. And then all I would have to do is go ahead and substitute back in what my u is here. So 2 times the ln of the absolute value of x plus 1 plus 1 over x plus 1 plus c. And I could go ahead and distribute in the 2 as well. So this could be rewritten as 2 times the ln of the absolute value of x plus 1 plus 2 over x plus 1 plus c. And there's my antiderivative. Right, the last couple are just application type problems. So one's an area under the curve, and then the next one is a volume problem. The area under the curve one is going to be a little bit different than the U substitution that we've been doing for the last couple. And we'll see why in 1 second. We'll see why this actually works out pretty nicely. So I know that I'm looking for the area under the curve of this ln of x over x on the interval from 1 to e. So the first thing I'm going to do is I'm actually just going to go ahead and look at what the graph of this function looks like, which looks like there's a little bit of area underneath the curve. So let me just do a quick little sketch of that. So my curve looks something like that. And my graph actually intersects the x-axis at the x value of 1. And then E might be, I don't know, somewhere over here. So we're looking for this area right here. So to set up my integral, I know my area is going to be equal to the integral from 1 to e of, and this is a top minus bottom here. So my top is actually this ln of x over x. My bottom is just 0. So my integral is going to be from 1 to e of ln of x over x dx. So we know that we'd want to use the U substitution. Generally, we'd look in the denominator, but if we set u to be x and we did the derivative of that, that's just going to tell us that du is equal to dx, which is not helpful at all with this ln. So in this case, I'm going to make an exception. I'm going to say, okay, well, what happens if we set u equal to ln of x? Let's see what happens. Du would then be 1 over x dx. And that would tell me that dx is going to be equal to x times du. So instead of substituting in for the denominator, if I substitute in for the numerator, I have that x that I'm hopefully going to cancel out with my denominator here. So let's go ahead and do that substitution. So u over x times, and my dx is x times du. And here's my cancellation that's going to happen here. So I'm going to end up with the integral of u du. And now I'm going to look at my lower and upper bound. So from 1 to e, ln of 1 is just 0, and then ln of e is just 1. So I'm going from 0 to 1, 0 to 1. And here, all I have to do is use a power rule. So when I do the antiderivative of u, that's going to be 1/2 u squared. And I'm going to go ahead and evaluate that from 0 to 1. So that'll be 1/2 times 1 squared minus 1/2 times 0 squared. And that's going to tell me that my area underneath my curve is actually just going to be 1/2. Right. And then the last problem is we want to find the volume of the solid obtained by rotating this region under the curve from 0 to 1 about the x-axis. So x-axis, we're going to be integrating with respect to x in this problem. I'm just going to go ahead and graph this quickly to see what the graph looks like. So it looks like this, and it looks like we're just going to be rotating the region right about here. So I'll just make a quick sketch of that on my paper. So from 0 to 1, be this region and the inside of here. And remember that with the volume, we're looking for a pi r squared situation. So my volume is going to be equal to pi times the integral. We have our x's from 0 to 1. And then my radius, again, is going to be top minus bottom. So top is going to be this 1 divided by the square root of x plus 1 over 0 squared. Which just ends up being this quantity of 1 over the square root of x plus 1 squared, because minus 0 isn't going to do anything with this value. And before I do any sort of integration here, I am actually going to simplify this, because if I raise both the numerator and the denominator to the power of 2, it actually simplifies things very nicely. That's going to give me 1 squared in the numerator is 1, And then this quantity in the denominator is really just going to be an x plus 1. And then at this point, u substitution is going to be pretty easy. This is kind of like the first example that we went over with the integration. So I'm going to call u x plus 1. I'll call du dx. Go ahead and do the substitution. So 1 over u du. And then I want to change my limits from 0 to 1. This is going to be actually from 1 to 2 now. So if I go ahead and do that antiderivative, that's going to be pi times the ln of the absolute value of u, evaluated from 1 to 2. And then using the FTC, that's going to be pi times the ln of the absolute value of 2 minus the ln of the absolute value of 1. And you can do one of two things here. You can condense if you wanted to. You could also know that the ln of 1 is 0. So this actually just simplified to pi times the ln of, and the absolute value of 2 is actually just 2 here. So that would tell us that our volume is actually just going to be pi times the ln of 2. All right, so now it's time for you guys to try some practice. Let me know if you have any questions.